Imagine this: you're sitting in your room, surrounded by gadgets and devices that have become an integral part of your life. Your phone, your laptop, the lights, and even the air conditioner all hum with the magic of electricity. But have you ever stopped to think about where this magic comes from? How did we go from candlelight and manual labor to a world where a flick of a switch can light up a room, and a few taps on a screen can connect us to anyone, anywhere in the world? The answer lies in the groundbreaking work of two men, Dalton and Michael Faraday, whose ideas and experiments laid the foundation for modern chemistry and physics. In the early 19th century, the world was a very different place. Chemistry was a mysterious and often alchemical field, and physics was dominated by the grand theories of Sir Isaac Newton. Newton had proposed that the universe operates like a giant clock, governed by precise mathematical laws. He believed that the forces of nature, such as gravity, acted at a distance, pulling and pushing objects in a predictable and orderly manner. This Newtonian view of the world was so powerful that it seemed to explain everything from the movements of planets to the fall of an apple. But not everyone was satisfied with this explanation. John Dalton, a humble schoolteacher from Manchester, England, had a different idea. He wondered why different gases mixed in the air behaved in specific, predictable ways. Why did water not absorb all gases equally? Why did some gases mix more readily with others? These questions led him to think about the fundamental building blocks of matter, what he called ultimate particles, or atoms. Dalton's curiosity was fueled by the work of Isaac Newton, who had speculated that the behavior of these tiny particles might follow similar laws to those governing the movements of planets. But how could one study these invisible particles? Dalton decided to focus on gases, which are the loosest and most mobile form of matter. He conducted experiments on the atmosphere, observing how different gases mixed and interacted. His observations led him to a revolutionary idea. The air was not a single vast chemical solvent, but a mixture of gases, each of which remained distinct and acted independently. Dalton's experiments culminated in a groundbreaking table of atomic weights. He took hydrogen as the unit of measurement, and calculated the relative weights of other elements. This table was a crucial step in the development of modern chemistry. By depicting atoms as tiny, solid balls, Dalton proposed that the Newtonian laws of attraction and repulsion could be applied to these particles. This idea was so radical that it was initially met with skepticism, even from prominent scientists like Sir Humphrey Davy. But over time, Dalton's atomic theory gained acceptance and became the foundation of a new, more precise understanding of chemical reactions. While Dalton was busy unraveling the mysteries of atoms, another young man, Michael Faraday, was making discoveries that would change our understanding of electricity and magnetism. Faraday was a self-taught scientist who began his career as a bookbinder's apprentice. His love for reading and experimentation led him to attend lectures by prominent scientists, including Sir Humphrey Davy. Impressed by Faraday's diligence and passion, Davy took him under his wing and offered him a position as a laboratory assistant. Faraday's early experiments focused on the relationship between electricity and magnetism. In 1821, he was inspired by the work of Hans Christian Oersted, who had shown that a current-carrying wire could deflect a magnetic needle. Faraday devised a simple apparatus using beakers of mercury, wires, and magnets to demonstrate electromagnetic rotation. This experiment proved that a current-carrying wire could rotate around a magnet and vice versa. Faraday's naive but visionary approach led him to suspect that there might be circular lines of force surrounding a current-carrying wire, suggesting that electricity and magnetism were somehow convertible. Faraday's experiments in the 1820s and 1830s were groundbreaking. He discovered that static electricity was not different from other forms of electricity, and that electricity could be used to decompose chemical compounds. These findings provided crucial evidence for the existence of electric particles and electric fields. Faraday's work challenged the Newtonian view of the world, which held that forces acted at a distance. Instead, Faraday proposed that forces were transmitted through fields of force, a concept that was difficult for many scientists to grasp. In 1831, Faraday made another significant discovery. He showed that a moving magnet could generate an electric current, a principle that would later lead to the development of the electric generator and motor. This experiment demonstrated the convertibility of mechanical and electrical energy, a fundamental concept in modern physics. Faraday's work also laid the foundation for the development of the field theory, which describes how forces are transmitted through space. Faraday's ideas were so revolutionary that they initially faced resistance from the scientific community. However, a young mathematician named William Thomson, later Lord Kelvin, recognized the potential of Faraday's work. In 1845, Thomson wrote to Faraday, suggesting that there might be a connection between electricity and light. Faraday was intrigued and set out to test this idea. On September 13, 1845, he passed a ray of light through a piece of heavy glass in the field of a strong electromagnet. To his delight, he observed that the ray of light was rotated, proving that there was indeed a relationship between magnetic force and light. This experiment opened up new possibilities for understanding the nature of light and the unity of physical phenomena. The work of Dalton and Faraday had far-reaching implications. Dalton's atomic theory provided a new framework for understanding chemical reactions and the behavior of matter. Faraday's discoveries in electricity and magnetism paved the way for the development of modern technology, from electric motors to radio and television. Their ideas challenged the prevailing Newtonian view of the world and led to a new, more sophisticated understanding of the physical universe. In the decades that followed, other scientists built upon the work of Dalton and Faraday. Gay-Lussac showed that when atoms combined, they did so in simple integer ratios. Avogadro proposed that equal volumes of gases at the same temperature and pressure contained equal numbers of molecules. Mendeleev developed the periodic table, which organized elements based on their atomic weights and properties. These contributions helped to refine and expand the atomic theory, making it a cornerstone of modern chemistry and physics. The story of Dalton and Faraday is a testament to the power of curiosity and perseverance. Both men were driven by a deep desire to understand the natural world, and were not afraid to challenge established ideas. Their work laid the foundation for the scientific and technological advancements that have shaped our modern world. The next time you turn on a light or use your phone, remember that these conveniences are possible because of the groundbreaking discoveries of John Dalton and Michael Faraday. Their legacy continues to inspire and guide scientists today, reminding us that the pursuit of knowledge is a never-ending journey.